Hi everyone, it's Katie here again. This is the last lecture I'm going to give you guys before we get together in the lab. And this lecture is focused on prepping for the laboratory. So again, I'm going to try to be quite practical about things. So today we'll talk a little bit about basic lab safety and about keeping a lab notebook. Make sure all of you guys bring a notebook to the lab when you come in next week. How to calculate concentrations and do dilution series, how to make solutions and use volumetric glassware, which you'll be doing in the lab, how to pipette appropriately, and how to set up a sample run. And don't worry if you've never done any of these things before. The whole point of this module is for you to get to learn about it and to get to practice. Ultimately, we are responsible to make the lab a safe environment, but you are responsible for your own safety in the lab. I will insist that you guys wear safety glasses at all times. And so given that you have to wear a mask at all times, you might want to think about taping down the mask on your nose so that your safety glasses don't get fogged up. If you're going to be working with something that produces fumes, you'll do it in the fume hood. We have one in our lab. I'll show you guys where the safety equipment is. The material safety data sheets are available for all the chemicals that you guys will be working with. There will be under no circumstances any eating, drinking, or smoking in the laboratory. You will not bring anything that remotely looks like a drinking container into the lab. And please pay attention to this point here. You guys on the lab day, regardless of how hot it is outside, you have to wear closed-toed shoes and you have to wear long pants. If you have long hair, you should tie it back in some way so it's not potentially draping over the lab bench. And we will provide gloves and lab coats for you guys to wear for your day in the lab. These are more things you can read through on your own. We will dispose of all waste appropriately. We'll provide waste containers for you guys during the lab. Nothing goes down the sink. We will neutralize the acid that you'll use for acid washing the glassware. And no one will ever get in trouble for an accident that happens in the lab. These accidents, no matter how minor, need to be reported so that we can take account for them. A couple of key things that will serve you well for our lab module, but any future lab work you do. Hot glass looks like cold glass. I've had this experience myself in picking up something and thinking that it was cool glass, and it turned out it was hot glass. It is not pleasant. And acid poured into water, acid into water, that's so sweet, right? If you ever need to make a solution with acid, you always pour the acid into the water. If you first put acid into the container and add water into the acid, so water into acid, wow, that hurts, ouch, I've just caused a big problem and burned myself and possibly others, all right? No matter what the situation, it's always acid into water. So laboratory notebooks, I'm hoping to get some out of storage for you guys and to give you an actual real lab notebook. And this is something that for those of you that go work in consulting or in the government or in industry, lab notebooks are considered really important. They're actually legal documents. They should be bound, meaning you can't just rip pages out. You must always number and date your pages. You make all entries in ink, so nothing should be erased. You don't cross things out using an eraser or correction fluid, you literally cross them out. Like as in if I had written this in my lab notebook, I wanted to cross out mistakes like this. You don't skip pages. If you have a large blank space, you just draw a line through it. And if you're working with someone else, you should put down their names. It's also good practice, although not legally required, to start each page with a sentence explaining what your goal is or what it is you're working on. You should make a reference to the standard operating procedure that you're following. So for example, the methods documents that I gave you guys online that you should have already read. And you want to enter the data and any information as you're doing it. So you don't write it on your hand or on a slip of paper and think, oh, later on I'll put this in my lab notebook. You use your lab notebook all the time. If you deviate in any way from the standard operating procedure, you should note that. You should describe the sample. Feel free to construct tables. And whenever you're recording a number, make sure you record the units, because when you're doing lab work day to day over and over, you will not remember when you go back what units you were working in. You can also, if you need to, if you want to print something, like for example, if you print a standard curve and then you want to use it, you can tape it or glue it into your lab notebook. A good test of how well you're keeping your lab notebook is If you gave your lab notebook to someone else and they sort of had roughly the equivalent technical background to you, could they repeat your work and get the same result just by following your lab notebook? And what more realistically, can you come back 6 months later when you have to repeat something and make sense of your notes? In terms of choosing an appropriate method, so in this instance for our module, we've chosen the methods for you. But at some point, you might be working somewhere independently in a company, consulting, industry, another university, whatever, and you might have to make a choice about what method you're going to do to conduct analyses. And there are some things to keep in mind. So cost being one, there's always a cost trade-off with certain methods. What equipment or expertise is required and what's available. The type of waste and the volume of waste generated, because that waste needs to be chemically treated and that's expensive and not good for the environment. What type of information is required and why? What level of sensitivity or accuracy is required? So essentially, what are you measuring and how are you going to use those data? And the last and important thing is to use a common sense approach. Consult the literature, look at methods, talk to people in the field, and find out what people have used in similar circumstances. Use SI units at all times. We'll use absorbance units, which doesn't have an SI unit. And so you'll sometimes see AU as absorbance unit for that, because we're going to use absorbance spectrophotometry for the nutrients. Concentrations are what we're going to be focusing on. We're going to be measuring nutrient concentrations. And this is a general measurement unit. Always is the amount of solute present in a known amount of solution. So it's some amount, for example, grams of nitrate or moles of nitrate per amount of solution, which is usually liters of water or kilograms of water. Here is a table that you can refer back to. These are common concentration units, their name, what they actually are, and the symbol. So molarity is one that we're probably going to use the most in this class. You will in some cases use normality, probably in the oxygen lab. Molality is something we don't use very often. You will see weight percent and volume percent, and sometimes ppm and ppb come up. Weight percent is expressed here as grams of solute per 100 grams of solution. It can also be grams of solute per grams of solution times 100. You'll sometimes see that as well. So if we have some examples to give you guys here. So if you have a solution of 1.5% weight per volume ammonium nitrate, it means that that solution contains 1.5 grams of ammonium nitrate in 100 mils of solution, probably water. If you dissolve 0.1 moles of calcium chloride in 1 liter of water, this gives you a solution of 0.1 moles of calcium and 0.2 moles of chloride. This is also known as a 0.1 molarity solution of sodium chloride. Notice the capital M here. And the reason for the different volumes is because calcium is 1 calcium, and here Cl2. You've got 2 Cl. So it's 0.1 moles of calcium, but Cl multiplied by this 2 gives you 0.2 moles of chloride. And there's just a note here, a technical note you can read on your own. Converting concentration units. I like to use the line approach. Other people have other approaches. If you have a solution of ammonia that's 28% to weight per weight ammonia, and it has a density of 0.899 grams per mil, what is the molar concentration of ammonia in this solution? So this is what you're given. You can refer back to the table and say, okay, weight per weight. That means 28 grams of ammonia in 100 grams of solution. Molar concentration, I'm trying to get to molar, which is the M here, which is moles per liter, right? Moles of ammonia per liter of solution. So how do I make that conversion? Well, I'm given the density. So here you have 0.899 grams of solution per mil of solution. So now you can cross out the grams. You can use the molecular weight of ammonia to convert from grams of ammonia to moles of ammonia. That allows you to cross out grams here. And if you wanted in moles per liter, you're now left with moles per milliliter, but you can use the conversion of mils to liter to cross off mils. So you're left with moles per liter, which is what you want, right? Molarity. So now you multiply everything on the numerator, everything on the denominator, divide, and you get 14.8 molarity. You also have stoichiometric calculations, and this will apply to the oxygen lab. So here, if you have a balanced chemical reaction, it gives you the stoichiometric relationship between the moles of reactants, that's usually on the left side, and the moles of products. So here, if you want to know the concentration of oxalic acid, it oxidizes to CO2 in the presence of iron 3+. This is oxalic acid here. You can oxidize it with iron, and you convert that oxalic acid to CO2, and you reduce the iron from iron +3 to iron +2. So if we have an example calculation here, so let's say 10.62 grams of aerosol or particulate matter were collected at Cape Point. And we extract that, so they're collected onto a filter, and we extract that with a solvent, and you oxidize the particulate matter. And it took you 36.44 milliliters of a 0.0130 molar solution of iron +3. Based on how much oxalic acid was oxidized there, how much iron 3+ it took you, you can calculate the weight % of oxalic acid in the aerosol sample. All right? So the easiest way to do this is in a stepwise reaction. And I'm actually going to post a follow-up little answer where I'll show you how you go through steps 1, 2, 3, and 4 to answer this example calculation. But for now, I'm going to move on. Okay, measuring mass. So this is when you weigh out things in the laboratory. This is a balance, this photo on the right-hand side. It looks very similar to the analytical balances we have in our lab. So you want to weigh out a chemical. Most of the chemicals in our lab are in powder form. These balances are digital, and they can be highly sensitive. It depends on what kind you're working with. So you want to put a clean and dry container. This is called a weigh boat, this little plastic thing here. And then you tear the balance so that it reads 0 with the weigh boat on it. So then you transfer some sample into the container, and the digital screen here will tell you what the weight is. When you want to measure volume, we do this in a bunch of different ways in the laboratory. When you're making a solution, once you weigh out the powder, as you did in the previous slide, you need some very well-known volume of deionized water. This is a graduated cylinder. It's probably the easiest and simplest way of delivering a known volume of liquid water. It's not super accurate, but it works. A pipette, which you'll see a bunch of them here and we'll teach you how to use in the lab, is a much more accurate way of delivering a known volume of solution, and we use these for fairly small volumes, so a milliliter, 500 microliters. A volumetric flask, which you see over here, contains a very specific volume of solution. In fact, it's labeled right on it. This is a 500 milliliter volumetric flask. So this is what we use to make standards. And so when you fill it to the line, which is here, you can see that little blue line across, it's highly accurate. And so we'll use this to make standards in the lab. You want to first transfer the reagent to the volumetric flask and add a little bit of water to dissolve it. And you want to keep mixing and add water and add the weight and keep mixing and keep adjusting it. And once it's completely dissolved, then you add water and bring it up to the line. And this is what the calibration mark is over here. So to make a stock solution, which we're actually going to do for you in advance because the laboratory stuff will take way too long if you guys also have to make all the stock solutions. But I think it's important for you to know how this works. So making a stock solution, you weigh out the appropriate amount of the solid or the powder on the balance. You put it in the known volume of liquid and dilute it. And then here, it says, so to prepare a solution with the desired molarity, you weigh out the mass, dissolve it in solvent, and bring to the desired volume. And if it's a volume %, you do it slightly differently. Let's get to it. It's more obvious if you actually look at an example here. So if I say the stock solution we need to make, we need 500 milliliters of 0.2 molar sodium hydroxide. First, you go and find sodium hydroxide in the lab, and you'll see the way things are organized in the lab. And it's not a powder, it's pellets. So you find sodium hydroxide pellets of whatever purity you need, and the method should tell you the purity. And now you're going to go weigh it out. But how many grams do you need, right? There's no grams in these instructions here. So what you need to do is figure out, okay, 0.2 molarity. That's basically 0.2 moles per liter. If I want to go from moles to grams, I use the molecular weight. So the molecular weight of sodium hydroxide is 40 grams per mole. So now I can cross out moles. And I ultimately want 500 milliliters, which is the same as 0.5 liters. Okay, and so here, liters cancel, and that tells me 0.2 times 40 divided by 0.5 is 4 grams. So you'll go to the balance, you'll weigh out 4 grams of these pellets, and then you'll put those 4 grams of pellets in a 500 milliliter volumetric flask. And at the end, you'll have 500 mils of a 0.2 molar sodium hydroxide solution. And remember, you need to dissolve the sodium hydroxide completely before you fill up to the line. Another example would be if you wanted 2 liters of 4% volume per volume acetic acid. So first you'd find where we store the acids in the lab, and this is concentrated glacial acetic acid. This is in the acid storage area. Because this is a concentrated acid, this is an example of something you'd work with in the fume hood, making sure you're wearing the appropriate safety attire. So a 4% solution is 4 mils of acetic acid in 100 mils of water. You want 2 liters of it, so times 2,000 mils, which is equal to 2 liters. So here this cancels, and it tells you that you need 80 mils of the glacial acetic acid. So you need 80 mils of this stuff. And so what you would do, and remember, always add acid into water. So for a total volume of 2,000 mils of solution, or 2 liters of solution, you actually want a flask with 1,920 mils of DI, all right? And then you're gonna add the 80 mils of acetic acid to that. So your total volume will be 2 liter, you'll have added the acid to the water, and at the end you'll have 2 liters of a 4% volume per volume acetic acid solution. Okay, once you've made the stock solution, which as I said will be done for you, the next step, and the step where you guys will have to come in, is you're going to dilute that stock solution. And so you want the total amount of solute to be the same before and after. So this equation, C1V1 equals C2V2, will definitely be your friend, and only for molarity-based solutions, which is what we're going to be using in the lab. So let's say you have the procedure for a primary standard. So you're asked to make 1 liter of a 5 millimolar nitrate standard. You calculate how much sodium nitrate needs to be weighed out so that when dissolved in 1 liter of water, it yields a 5 millimolar solution. So you check what molarity is. It's moles per liter. The milli prefix is 1,000th of a mole. So 5 millimolar equals 0.005 moles of solute in 1 liter solution. So this is what you've just figured out here. You need to know how many grams to weigh out, and you've got how many moles you want. And so you wait until you find what kind of nitrate standard did you find in the lab. You'll find sodium nitrate. So the molecular weight of sodium nitrate is here. And so you use the line method again. So you know how many grams per mole, that's your molecular weight. You cancel moles. And it tells you that you need 0.42497 grams of this sodium nitrate standard in 1 liter to end up back at your 5 millimolar solution. So you find the sodium nitrate, you weigh out that amount on the weigh boat using a balance. You've put a little bit of water in your volumetric flask. You add some of the sodium nitrate that you weighed out, you shake to dissolve, you add a little bit more, you shake to dissolve. Once it's all in there and all dissolved, then you finish filling up your 1 liter flask to the line with your DI water. And that's your primary standard. So you have a primary standard, and now this is the part that you guys are going to have to do. You're going to have to make secondary standards. So in the lab practical, this is just an example. Let's say you need 500 mils of a 100 micromolar secondary standard. Okay? And so what you would do is use your C1V1, C2V2. Okay? So this is your useful thing. So you want and that's your C1V1 is what you want. You want 100 micromolar solution, and you need 500 milliliters of it. All right? What you also know is C2, which is the stock solution you have. You know that you have 5 millimolars of a stock solution. What you don't know is V2. How many mils of that primary stock standard do you need to end up with a concentration C1? You also need to make sure at this point that C1 and C2 are in the same units, and V1 and V2 are in the same units. So note here, this is in millimolar, this is in micromolar. Okay, so if you rearrange, you have 500 mils times 100 micromolar equals 5,000 micromolar times X mils. If you solve for X, you get 10 mils. So what this tells you is if you pipette 10 mils of your 5 millimolar primary nitrate stock solution, and you put it in a 500 ml volumetric flask, and you fill the rest of it to the line with DI water, that 500 ml volumetric flask now has 100 micromolar of your secondary nitrate standard. And I'm going to give you guys some additional practice equations, and we'll do this as a group, of course, when we actually get into the lab. So once you've made your secondary stock solutions, you have to think about how you want to do your analyses. So this requires some thought about the instrumentation being utilized, the sample and standard integrity, so how long they can last, the blanks, the sample volume, stability, etc. So it's not always going to look the same every time you analyze something. Typically, standards are run from low to high concentration, and this helps to avoid carryover. So imagine if you're analyzing your highest concentration standard first, and you accidentally get a drip of it on something. When you go to analyze next to lower concentration standard, that drip will give you a lot of contamination. The other thing is that samples are almost never analyzed in their experimental order. So if you're running a time series, you choose samples T0, T1, T2, you wouldn't run them in that order, just in case there's any sort of drift in the instrument. We're going to want to run blanks first and throughout, and we're going to want to run a couple of check standards. The other thing is that samples should be analyzed in batches. So you don't just want to run a bunch of standards and then analyze 500 samples. You want to analyze a batch and then stop and do a blank and stop and do a check standard. The other thing to keep in mind is that a certified reference material should be run early after the standard so you can make sure everything's working before you waste your sample volume. When you're working with seawater, there's a couple things to keep in mind. Because you have a high concentration of ions, it's a high ionic strength solution. And so there can be very complex matrix effects, which we talked about a little bit when I was talking about ammonium. And that the nutrient concentrations, which are the things you're usually trying to learn when you're doing biogeochemistry, are much, much lower than the salt concentrations, which is a bit, complicates things a bit. So some tips when sampling for nutrients. You'll use a CTD or a Niskin bottle. You never want to grab the bottle by the opening or touch the stoppers with bare hands. You always want to have gloves on. You want to use screw cap HDPE sample bottles that are leak proof, preferably with unlined caps. You always want to rinse the bottle with seawater. And so you pour some seawater in the bottle, shake it around, empty it out, pour some seawater in the bottle, shake it around, empty it out, and then take your sample. Frequently, we filter nutrients samples through a 0.45 micron pore size filter, so you want to get rid of the biology. And you don't want to overfill the bottle. You fill the bottle about to the shoulder, because when you cap it and put it in the freezer, it expands. For those of you who have ever left a soda bottle in the freezer will know, it can explode. You always want to wear gloves, and you want to determine the concentrations as soon as you can after collection, or freeze the bottles at -20 if you have to. Something else to keep in mind in terms of wearing gloves is that your fingerprints can cause contamination. So when you pour some sample into a small cup, if you get it on your skin, depending on what's on you, there are some things you can contaminate. So something to keep in mind, ammonium is super easy to contaminate. If you look here at the relative contamination, if you just get a little bit of finger on a 5 ml sample, 90% of what's in your bottle is contaminant. Nitrite, which is not really around very much, is really difficult to contaminate. Nitrate, a little bit easier. Phosphate, a little bit easier. Okay, so it's just things to keep in mind. Another general tip, ammonia is in everything. Ammonium is one of the more difficult nutrients to measure, and it's also fairly low in concentration. Perfume, cigarette smoke, all these things, leaving your sample open because there's gas exchange with ammonia, all these things can contaminate. The other thing with seawater is you always need to shake after thawing and shake it like you mean it. So if you think about sea ice, how sea ice forms, you have brine rejection, right? So that's why the ice itself is fresh and the salts get left behind. If you think of your sample bottle, your frozen nutrient bottle, as basically being like a little sea ice system, if you don't completely thaw it, what you're going to end up with is a very fresh chunk of water in your bottle and all of your ions in solution. And since we measure ions as mole per liter, this is going to be, you're going to get the wrong concentration. It's going to be way too high because most of your liters of water are in the ice chunk, that's an ice cube, and not in solution. And so you want to make sure you always completely thaw it. And again, a lot of these things might sound a bit foreign to you guys, but hopefully it'll start to make a bit more sense when you're actually doing it practically, and then you can go back to these slides and use them as a reference.